The last text transform I want to discuss is the Burrows-Wheeler-Transform, which is a very interesting example also from a historical perspective. When it was first invented, it was thought not to be of interest. It was of theoretical interest maybe, but it wasn't published for almost a decade because the inventor thought it's not practical. Computers don't have enough memory to ever use this on interesting size inputs. But then 10 years later, the hardware has changed, computers had improved, the memories have grown, and suddenly it was feasible to do this for interesting texts. And nowadays, essentially, okay, I don't want to say anything wrong, it should be 30 years now. It's one of the key components both for compression and for text indexing and for many other tasks that build on top of that. So it shows you that even though some concepts are purely theoretical, of pure academic interest for some time, they might well turn into a very practical solution at a later time, because data sets and computers grow so fast, it's very hard to discern something as impractical. So much for the historical context and relevance of this. In the context of compression, it's a text transformation. And it's a very interesting one because the coded text, or the result of the transformation, is the same length and the same characters as the input text, but the characters are shuffled around. So you can essentially realize the BWT by taking the characters and swapping them around. But somewhat magically, the output of the BWT often is compressible with the move to front heuristic. So exactly the way I showed it to you just before. Combining these two things will lead to the best known compression methods for English text and many other types of inputs. A downside that we'll discuss at some point again also is that unlike the other methods that we've seen, we need the entire source text to compute this transformation. And we have to keep the entire source text in memory. That's the main reason why it was initially deemed not practical. So if you want to compute, if you want to use this in a stream sense, you can apply it to blocks of a certain size and encode the blocks individually. But you would still need the entire block in memory. There's a program bzip2 that if you're on Linux, you might just have that already installed, or you can install it from repositories. And that one does precisely the BWT, followed by the move to front heuristic, followed by run length encoding, because as you'll see at the end, this combination BWT followed by move to front often leads to long runs. And finally, Huffman encode the output of the run length encoding. That's what's done in the bzip2 program. And if you apply this to the just plain ASCII text of the Bible, you see that that's GNU zip. So it's essentially something Lempel-Ziphy. This is 7-zip, which I think is one of the best general purpose compressors for data, for just files. At least I usually opt for 7-zip if I don't have any specific reason to do something else. But here the bzip2 is actually smaller than 7-zip. So if you compress natural language text, definitely consider bzip2. It's quite possible that it beats the other methods. All right, so I guess now you're fairly curious what this BWT is and how it works. The Burrows-Wheeler-Transform talks about cyclic shifts of a string. So to explain what that is, imagine you have a certain text, and now you write this on a circle. Time flies quickly, just written around the circle. a cyclic shift is keep this cyclic string as it is, but instead of starting here and ending there, you just shift this cut point and you start here and end there, and that gives you flies quickly time, which is a valid English sentence, interestingly enough. Okay, but that's not the point. If on top of this, before you do this circle, you add an end of word character, like we've had it many, many times before, you can always recover the original string, because the end of word marker obviously marks the cut in the circle for the original string. So you can always you can always go back and forth to these. You can go to a cyclic shift and go back to the original string. The Burrows-Wheeler-Transform now consists of 3 simple steps. First of all, you take your input text S and you write down all cyclic shifts. That means you just write S like this. And well, to be fair, you do the dollar trick. So you add the dollar to S. I should have put that here. And then for every possible position, you make the cut once and you write all those cyclic shifts down. That gives you a list of strings, and that list of strings is sorted, just lexicographically. And finally, the Burrows-Wheeler transform of the input text is the last character of all those cyclic shifts. Example. Here's a text, Alf eats alfalfa. Again, valid English text. You write down all the cyclic shifts. So I added the dollar is already here. You can get those by just always shifting one character to the left. So here you take the A, you move it all the way over, and then it gets here. So here's your A, and then it starts one character later. You do this blah, 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 for all possible shifts until, if you see here, the dollar moves one position to the left in each step, so until it's the first one. That's easy enough. Then you sort all those strings. Then you know, well, the dollar is smaller than everything else, so that comes first. Then comes all the spaces. Among those, it's sorted according to the second character, and so forth. Lexicographic ordering, as we've discussed it before. And the last step is you read the last column of this matrix of characters top down, and that gives you the BWT. All right, fairly simple definition. Not at all clear why this would be helpful, and it might also not be clear that given this thing, you can actually reconstruct this text. But both is true. BWT is very useful, and it's invertible. Let's talk first about how to compute it efficiently, because this sorting step, it can be done using a general purpose sorting method, but that's not super effective. It could in the worst case be n squared, because comparing two of these cyclic shifts could take linear time if they have many repeated characters. But as my incorrect saying already exposed, there's a connection between these cyclic shifts and suffixes. That's very simple. A cyclic shift contains this dollar, so if you just forget everything behind it, it's a suffix. The beginning, the first part of the cyclic shift up to including the dollar is a suffix of the text. And sorting the cyclic shifts is the same as sorting suffixes, because you never look at characters behind the dollar. There's no way how two different suffixes or two different cyclic shifts would align the dollar on top of each other. Then they would be the same. So there's no way you will ever have to look behind the dollar in any of these strings. So you might as well sort suffixes instead of cyclic shifts. And of course, we know how to sort suffixes. We spent a whole lecture on that in Unit 6. So we know that this can be done in linear time, and I've actually shown you how. And the precise connection between the two things, if you want to be formal, is the character, the BWT here, the character, is given by whatever the suffix array at that position is, and then go one position to the left. So let's see that for an example. Say we want to see what the second entry in the BWT is. We would go to the second entry of the suffix array, that's 8. L1 is 8. That means this is the suffix 8 is what occurs here. That's the second smallest suffix in lexicographic order. And now the BWT is this character, S. That's what we want. How do we get this S? Well, it is the character that comes right before this suffix, because it's a cyclic shift, remember? So alf eats alfalfa. If the suffix is just space alfalfa, S is what precedes this. And that's why we take exactly the character before the beginning, the starting position of the suffix. That's why we have this -1. L1 is 8, and that's the suffix starting at position 8. So it's S8 as we used to write it. And what we need is this, the 7th character in the string. So if you count 0, blah, 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 that would be at position 7. All right, so that's the formal connection between BWT and suffix array. So being able to compute the suffix array in linear time is sufficient for computing the BWT in linear time. Also in this picture, we can get a feeling for why the Burrows-Wheeler-Transform helps with compression. The first observation is that sorting groups the characters in the BWT, by their context, by what follows them in the text. So, for example, LF is always in this string, alf eats alfalfa. Any occurrence of LF is preceded by an A. Here's LF, there's your A. Here's LF, there's your A. Here's LF, there's your A. That also means if I see in the BWT an A, for 3 of them, there's LF behind it. And because that following context is the same, that means the suffixes here will be adjacent, because they're those are the same, and then they're grouped together in the suffix array. Because of the sorted order, if they start with the same thing, they have to be together. That means in the BWT we have a run of A's. The same following context groups these A's in the BWT together to form a run of length 3. And this is the basic magic behind the BWT. It groups characters by the following context. And well, this example is not that long, so it's hard to see more instances of this. So you'll have to live with this small example. Another one that's induced by this is there's a run of L's here, and that comes from the fact that an L is followed by F in 3 instances. That's actually all in this example. Right, again, so there's a common context, which is the same as here. We have 3 occurrences of alf, and that means we also have 3 occurrences of lf. Okay, that's for why the BWT will have runs of A. Now, more generally speaking, if the context is not exactly the same, it would still mean that a similar context will be grouped close together in the BWT. And that would still mean that there's local clusters of characters, in the sense there's areas in the BWT where certain characters are much more frequent than others. And if you remember, this was exactly one of the prime examples where the move to front heuristic helps us to exploit these local clusters. It was something that Huffman coding by itself couldn't pick up, but with move to front first, it becomes exploitable. And if you have exact repeated substrings, that's what I just illustrated with the ELF, then we have runs of characters. And again, this can be exploited with run length encoding. So I told you that we use BWT, then move to front, and that doesn't destroy runs. So these will be picked up by the run length encoding. So this is pretty cool. We found this amazing text transformation that magically helps us to exploit common contexts of characters. And I at least gave you an informal, intuitive reason why it helps for compression. But if we want to use this, we also have to decode it, and we have to be able to recover the original text. How should that be possible? It seems like when you sort things, you completely forget what the unsorted part was like. But not so for the BWT. There's a really magic algorithm for doing this. If you just see this, it seems to magically work. So the magic algorithm is as follows. You're given the BWT, just this array of characters. Now you do the following. You create pairs for every position in the BWT. So here's the example input. You create a pair, the character and its position. So just A and 0, R and 1, D and 2. So very straightforward. Everyone can do this. Then you take these pairs and just sort them stably with respect to the first character. So you don't sort the entire list. Well, it's actually already sorted by the second component, so you don't have to do anything for that. But what's meant by stably sorting, again, is all the A's in the first position are grouped together and come at the appropriate position, and the second components are also still sorted. So you could say you just sort the whole thing, but what you really have to do is just sort by the first entry, the character, because the second part is already sorted if you create the list in that way. This is all fine. This is not very magic. The magic step comes now. You take this sorted list of pairs and you interpret it as a representation of a linked list. You have a character column and you have a next entry column. And you just walk through this as follows. You start with the first position, and it tells you the next character to read is at position 3. So you go to position 3, and you find an A there. So you put an A in the output. The next position is 7. So you go to 7, you find a B, you write your B, and it tells you the next position is at 11. So you go there, you write your A. Next position is 4. You go to 4, you write your A, and you go to position 8. There you find a C, and you go to 5. So this is exactly how a linked list would work. It tells you what the current element is and where to go next. And you just jump to the appropriate index in the next for getting the next character. That's just all there is to it. And if you walk through this until the very end, you know when you're done when you read the dollar symbol, because that's the end of the string, and then you decode this to abracadabra. That really looks magic, and I guess I should really stop here and explain you next time why on earth this really decodes the BWT. So this shows you that it's doable. You can go back, take this source text, apply the BWT with just sorting all the cyclic shifts, and you will find that this is the correct Burrows-Wheeler transform. And I guess you'll have to wait 3 weeks with this cliffhanger before I'll tell you why this is the right solution for the inverse BWT.